Bismillahirrahmanirrahim. Assalamu alaikum. So today inshallah we'll start a new chapter under the topic of image processing, which is about image arithmetic. Okay? So here in this image arithmetic we'll see what are the basic arithmetic operations that we can do in images. Okay, and we'll see some examples of these operations together. Okay? So maybe this chapter and the chapter that comes afterwards, which is about the logic operations as well as affine transformations. Both of these two chapters actually they depend on some linear operations that we can do in these images. Okay, they are very simple, but we need to understand how things are done. So, if you look at the to do the image arithmetic, actually we need arithmetic operators, okay, that can operate on images. If we look at the images from the point of view of the MATLAB, we can see that the image actually is in the form of a matrix, right? Okay. So once I have converted my image in the form of a matrix, then after that I can do on it any matrix operations of the operations that we know. Okay. Whether arithmetic operations, logical operations, etc. Okay? So we will say that arithmetic operators can operate on images very much the same way as for matrices, except for some few considerations that we'll consider it as we go. Another thing here, we say that the image arithmetic works on pixel by pixel manner for two images of the same size. So for example, if I want to add two images together, each two corresponding images with respect to their locations will be added together, okay? Or subtracted, or multiplied, okay? Or maybe divided, as we'll see in the coming examples. Okay? Also here we say that another form of image arithmetic is to apply a scalar over the image matrix. For example, I want to amplify the intensity of all of the pixels by a certain factor. So in this case, I will multiply a scalar value, a single value, with all of the pixels that I have in this image. Either to make my image brighter or darker or whatever. Okay? Okay. Also here we say that the main or fundamental arithmetic operators, okay, like the arithmetic operators that are used to either addition, subtraction, multiplication, and division. And each one of these operators actually can be used in certain specific applications. Here we say that for n tuple images, the operation takes place for each pixel with corresponding pixel in the same layer. What do I mean by n tuple? Here, tuple, it means layer at the same time. Can you give me an example of an image that consists of several layers? Like the color image, okay, like the RGB image, for example. Okay, in this case, I have a layer for each one of these colors. Like the YCBCR, okay? All of these color images in which we can represent the pixel by, let's say, 3 bytes, okay? That can represent either RGB or YCBCR. In any one of these representations in the color space, actually this is called an n-tuple image or a multi-layer image, okay? Okay, here we say that we'll start dealing with or we'll start presenting each one of these operations. I can use it in which type of application. So here, if we start by the addition, it's mainly used for changing the intensity of pixels, merging images, if I have two images that I want to merge them together, okay? Adding contents to an image, and some other type of operations, okay? I want you to be able to understand how this will happen. Yes, have a question? Yes.
Base scale, is there considered as one layer?
Yes, in this case it's considered as one layer, yes. Yes. So here actually the index is a special case. The index is a special case. It's but in general we consider it as one layer. Okay. So here we say that the addition is used for changing the intensity of the pixels. Okay. So this means that if I have, for example, a certain, let's say, matrix, or let's say a certain scalar value, and I want to add this scalar value to all of the pixels that I have. So this means that the intensity will be increased by a certain level. Or let's say I want to subtract it from all of the pixels. So in this case, the intensity of all of the pixels will decrease with the same level. Right? So in this case, I can change the intensity by adding or subtracting a scalar value. Right? Let's say here we are talking just with addition. So here by adding this scalar value, I can increase the intensity of the pixels. Another thing here is merging images. Okay? I can add two images together in order to have a merged image, a resulting image that can have the features of both of these two merged images. Okay, as we'll see later. Also here, adding contents to an image. Let's say, for example, I have a big image and I want to add a certain content in a certain location inside this image. So this also can be done using addition of matrices. Okay, and we'll see examples of this. Another type of operation is the subtraction. Okay, and this subtraction, it can be used for target detection. How can I do this kind of target detection? Or let's say object tracking. Okay, how can I do this? Actually, first of all, here it will depend on the second item that is represented here, or that is mentioned here, which is called the background removal. So if I'm interested in detecting a certain object in this image, if I succeed in subtracting the background from this image, I will have the object. Okay, so this can be done by subtraction. Okay. Also, here we say that the inter-frame differentials. For example, if I have a video sequence of a certain location, let's say, here I am capturing the video of this room, and I want to know who was the person who has entered in this room, at the time of 8:05, let's say. Okay? So actually, in this case, I will see all of the tracks that I have, or all of the image frames that were captured, okay? And I will make some sort of subtraction between the successive frames. If I have, for example, 0 difference, this means that these frames are similar. Okay? If I have a non-zero difference, this means that I have a difference in both of these frames. This difference can be either as a result of changing the lighting, of the intrusion of a certain person inside the room, and so on. Yes?
And this is not even if it's a video?
Yes, sure. And actually this is done with videos in general. Here we say that it is inter-frame differentials. Inter-frame, this means that I am making some sort of subtraction between successive frames. You see what I mean? Right. Also here we say that I'm removing artifacts from an image by subtracting, let's say, a certain level of intensity that corresponds to the noise. In this case, we can remove some sort of artifacts. Of course, the removal of the artifacts, these are the things that are added to the image and they are undesired. Okay? The removal of artifacts is not that simple, but this is one way of doing things. Okay? If I want to remove these artifacts, I can apply filters. I can apply much more complex, let's say, processes.
Is it noise?
Yes?
Is it noise in the artifact?
Can be, one of the things is the noise. Another thing can be in the form of a distortion, okay, that is related to the capturing device itself. Or let's say while I'm capturing the image, I have, my hand has moved, so in this case I will have a blurring image. Okay, so all of this can be considered as artifacts. Okay, they are of different types, in fact. Multiplication and division. These are the last two arithmetic operations that we can do in images. Multiplication and division can be used for scaling and normalizing applications to make the image more visually appropriate. Let's say, for example, I have captured an image in, let's say, in an environment that was not correctly illuminated, or that has no enough illumination. Okay, so in this case, I will have my image will be dark. Okay, so in order to improve the quality of the image, I can make some sort of multiplication and division operations in order to use the whole range of possible values that I have, from the 0 to 155 for each pixel. Let's say, for example, the image that I have captured, it has the range of the values of the pixels is between, let's say, 10 to 100. I can expand this range. Okay, I can expand this range by doing this kind of scale multiplication together with some sort of addition and subtraction and so on. Okay? Right? So all of these operations, actually, they are linear operations that can be done directly on the pixel, pixel by pixel. Okay? Here, we say that a linear combination of images is also possible, which is the case of the merging of image, as we'll see later. I can merge image, and I can merge these images with different proportions. This means that the resulting image, it will have 80% of it will come from the first image, while 20% will come from the second image. And we can do such kind of merging with specified, let's say, ratio of merging. Here as well, this concept is very important. This one is related really to the properties of dealing with the different types of image mass types, which we call it the overshoot and undershoot in terms of pixel values. Here we have said that the pixel value I will apply with, let's say, an operation of addition, subtraction, multiplication, division. So maybe I may reach the ranges, or let's say the boundaries of the ranges of the values of these pixels. Let's say, for each pixel, I have the range for an unsigned integer with 8 bits. It ranges from 0 to 255. Right? Maybe, for example, I have something like this. I have a pixel value of 100. Okay? And this pixel is multiplied by the value of 5. So what will be the result here in this case? 500. But 500 is above the maximum level. So what will happen here is that this value it will be saturated at 255. Clear? Okay? This is the case of the overshoot. The undershoot is the same thing. For example, if I want to subtract, let's say I have a value of 50, the pixel has the value of 50, and I want to subtract from it 100. So this normally should give me how much? Negative 50. But since this type is an unsigned integer with 8 bits, so it will be represented with 0. Okay? This is what's meant by undershoot. So here we say that the overshoot when the value tends to exceed the maximum value, and the undershoot when the value tends to go below the minimum value. So in this case, it will be saturated to the maximum value and the minimum value, respectively. Yeah? Okay? And we can test it in MATLAB after a while. Do you have any question about what we have introduced so far? So all of these things actually they are very simple and straightforward. So here in this slide we see the operator basics, how the operators are applied. So either I have two matrices or two images of the same size, and the operation will be done with each two corresponding pixels in these images. For example, here if we take this example on the left, I can apply, let's say, the operation on pixel A with the first image, with pixel J in the second image. Okay? And the same operation will be applied between pixel B and pixel K. Okay? And this operation as well will be applied between C and L, and so on. Right? So in this case, if I have two matrices on which I want to make this operation, they should be of the same size. Okay? And the operation will be done on the corresponding pixels together, whether it's an addition, subtraction, multiplication, or division. Or it may be something like this example on the right-hand side. Here we have a scalar value, alpha, that will be applied on all of the pixels that we have. So for example, I can say alpha plus this matrix. So what will happen is that the result will be A plus alpha, B plus alpha, C plus alpha, D plus alpha, and so on. So alpha will be added to all of these pixels, or it can be multiplication, division, subtraction, or whatever. Okay? So here if we look at the types of operators, actually we have here so here we have algebraic operators, which are the addition, subtraction, multiplication, and division, and we have the logical operators, which we'll deal with in the next chapter. Like, for example, I can do logical operations between two images together. This is very important. Like, for example, the AND operation, the OR operation, the NOT, the XOR. And these operations can be done in several operations. Let's say, for example, if I want to make masking of a certain region in this image, okay, and I will apply, let's say, for example, the operation that I want to do on the unmasked part only, okay. Or I can, for example, take part of an image and put it in another part in another image, okay, and so on. So for the first three types of operations, we'll see some examples today, and for the logical types of operations, actually we'll see their corresponding examples next lecture, inshallah. So, yeah, if we talk about the addition is very simple. If I want to draw its corresponding flowchart, it will be something like this. I have two images, P and Q. Both of them that are having the dimensions m by n, okay? And I have a loop here, right? So what will happen here is that for each pixel ij in P and Q, they will be added together in order to produce the pixel ij of the resulting image R. Okay? Straightforward. So this is for the first case. The second case here is adding a scalar to the image. And we have seen how this will happen. Okay, this scalar will be added to all of the pixels that we have. Okay. So it's like an offset, as it's saying here. Another thing here for the subtraction, same thing, similar. Okay. So either I can have two images that I want to subtract them from each other, or I have an image that I want to subtract a scalar from it. Okay. If, let's say, the values of the pixels of the image are of type double, okay, then it's better to put the result of the subtraction between absolute, let's say, operator. So in this case, actually, I will avoid the negative or the appearance of negative values. Right?
So,
Yes?
there will not be an undershoot here?
No, actually, here the undershoot will be represented only with the unsigned integer 8. It will be handled in the case of the unsigned integer with 8 bits. But here, if it is of type double, you need to handle it yourself as a programmer, the overshoot and the undershoot. Okay? So either you can take the absolute value, or you just detect the values or the resulting values here. If it goes below 0, just force it to be equal to 0. If it goes above 1, force it to be equal to 1. Okay? So it's up to you, depends on the application itself. One of the things to do here actually is to use the absolute value. And here, of course, we are assuming that P and R, these are the two images on which we are doing the operation, they are of the same size. Okay? Here we say that the C is a scalar constant, of course, and the absolute values, of course, are calculated in order to avoid negative values in case the image is represented using the double value. Okay. For the multiplication, here we have two types of multiplication. We have the pixel by pixel multiplication, which are widely used in the image processing, and we have the regular matrix multiplication that we know from the calculus course. Right? So here, these are the representation of both of these two multiplications. Of course, here, in order to make the first type of multiplication, P and R should have the same dimensions. Okay? While the second one here, actually, the number of, let's say, columns in the first matrix should be equal to the number of rows of the second matrix. Okay? This is the normal matrix multiplication that we are used to. Or we have the simplest type of multiplication, which is the scalar multiplication. Multiply scalar value by all of the pixels that I have inside this matrix. Okay? For the division as well, here either I can divide, let's say, the pixels of one image with the pixels of another image. In this case, it will be pixel by pixel. Here as well, we have division by a scalar quantity, division by a certain constant quantity, or we have the normal division of matrices using the matrix manipulation or the matrix that we have studied in calculus, which is that when I say Pij divided by Rij, this is equivalent to Pij multiplied by the multiplication inverse of Rij. Okay? But this is it's not widely used in case of image processing. In image processing, we in general we use the first two types of divisions. Okay?
So,
Yes?
in the multiplication, why we have two images, they should be the same size, and we have two matrices, the columns should be the same as the rows.
You mean this one?
يعني شيء فرق يعني both are.
This one here actually, P and R should have the same dimensions. This means that the number of rows and number of columns, number of rows in the first matrix should be equal to the number of rows in the second matrix.
Okay.
And number of columns should be equal to the number of columns.
Yes.
So that in order to make that pixel by pixel multiplication. Okay? The second one here is the normal multiplication that we are used to, multiplication of matrices. You remember this? No, the other one here is pixel by pixel. This is element by element. So for example, I will have something like this. Let's say I have a matrix P and matrix R. If I want to make pixel by pixel multiplication, so in this case, if this one has the dimension of 3 by 2, this one as well should have the dimension of 3 by 2. Okay? So in this case, this element, the element in the first row, first column, will be multiplied with the element in the first row, first column. Okay? The element in the first row, second column will be multiplied by the element in the first row, second column. Okay? But if I will apply the regular matrix multiplication, okay? So in this case, I will have something like this here. Let's say I have, this is P, this is R. Okay? For this matrix, I have a restriction. Okay? The dimension of this matrix is what by what? Number of rows by number of columns. Here, this matrix should be equal to 2 by something. Okay? 2 by 4 for example. Okay? So in this case, I will have something like this. Okay? And the operation here will be done like this. In order to generate, actually this will generate a matrix of what dimension? 3 by 4. So this means that here I have 3 rows and 4 columns. If I want to get or to compute this element, which is the element in the first row and the first column, the resulting matrix, this will result as a result of the multiplication of the first row in the first matrix with the first column in the second matrix. So I will multiply this by this and this by this.
How the program can differentiate between this and this is at the end this is a matrix and this
It's very simple. Here actually, if I will use the asterisk, just the asterisk, this means that it's a regular multiplication. If I will use dot asterisk, it's a pixel by pixel. Okay? Straightforward. Okay? And it's up to MATLAB to verify whether, for example, these two matrices can be multiplied or not. Okay? In any one of these cases. Okay? Clear?
Yes.
Type. Let's talk about the blending, okay, which is the merging of two images together. How can we do this? It's very simple. The idea is very simple. Here we say that we have an operator. Let's say it's a blending operator. Its corresponding mathematical representation, it is something like this. Here, first of all, I need to define a scalar value, which is a fractional value between 0 and 1. Okay? And this C, actually, it will give me an information, provided that I have two images, P and R. I can specify the blending, it will be how much percent. This means that the resulting image will be constituted with how much percent of the first image and how much percent of the second image. So, for example, here, if I want 80% of the P and 20% of the R. So, in this case, I should put the C should be equal to 0.8, and 1 minus C here will be equal to what? 0.2. Okay? So, in this case, here, the resulting image Q will be equal to 0.8 of image P plus 0.2 of image R. Okay? If I want, for example, 60 and 40, so in this case I will put here 0.6 and 1 minus 0.6, it will be 0.4. And so on. If I want, for example, equal contribution, so I will put C is equal to 0.5. So it will be 0.5 P plus 0.5 R. Clear? Okay? So this is how it is done. And here in this slide, we will see here that we have the other type of operation which corresponds to the logic operators. That we will see their examples, inshallah, next lecture. Here as well, the logical operators, this ampersand, this means that I will make an AND operation between each two corresponding pixels. Okay? So you will have pixel by pixel operation. Here are of the same size, of course. They should be of the same size. They should be of the same size. Here, this vertical line, this is the OR operation. So I have the AND, I have the OR, and I have as well the exclusive OR. Okay, the XOR. Okay, and finally we have the NOT. And here the NOT, of course, it's a unary operation. This NOT will be applied on one matrix. Okay, so in this case it will just convert to values. Does this mean that I have images of logical type? This means that each pixel can be either true or false. Yes. Which is which type of images? The black and white. Right? And actually here, as you will see, the type of the matrix itself can be of logical type. It's not double, it is not unsigned integer 8. It is of logical type. Okay? And of course here the logical true is represented by 1, and the logical false is represented by 0. Okay? Right. Here, if I want to apply it, let's say, on an image of unsigned integer 8, I want to get its knot, I want to get its inverse. How can I do this? If I have, for example, my image is an 8-bit grayscale image, and I want to get its inverse. Can I get its inverse? Okay. For the black and white, it's straightforward. This means that each white pixel will be represented by black, each black will be represented by white. Here, actually, if I want to apply it on the grayscale image, I will subtract the image from the maximum value, which is 255. And you will have the negative effect, in fact, of the image. Okay? Right. Now let's look at the examples in MATLAB. So we'll switch to MATLAB here. Okay. Again, let's increase it a little bit. Space, I think. Okay. So now let's start by this example. In the book, actually, the example is in chapter 3, example number 8. So here he's taking something like this. He has two images, P and Q. One of them is called smile 1 and the other one is called smile 2, and he just wants to add these two images. Okay. So here we'll find something like this. We have, of course, here I will read the image. P equals I will read on line 4. Then after that, here I will show the image. Then I will read the second image and put it in the matrix Q and show the image as well in another window. Then after that, here for the image processing toolbox, we have the function IMAdd, which is function that is responsible for adding the two images together. And the result actually will be put in R. Then after that, here he has shown the R, right? Then after that, he has shown the R after adding 100. What will be the result here? What do you think will happen? It will become brightness. The intensity will increase. Okay? The intensity will increase. So here, if we take this to let's first of all, as I want, let's close any figures that are opened. Let's clear the workspace just to make things easier, and clear the command window. Then after that, here we'll take this, make a copy, and these are the resulting images that we have. Okay, so this is the first image, and this is the second image. Okay, of course these are colored images. Okay, right? Of course these are colored images, and as I can see from here in the workspace, in this part of the workspace, I have an information about the let's say the sizes of these images. We have each one of these images actually has the size of 720 by 160. Okay, number of rows and columns. So these two images actually they can be added together. Right? These are multi-layer images that are having RGB. So each value in its corresponding layer will be added to its corresponding element in the other image in the corresponding layer. Okay? So here, if we go back to the code, now R is computed as image add P and Q. Now if we want to show the R, row C, this is the resulting of the R. Okay? Of course here, as a result of the addition, the brightness, the overall brightness of the image actually has increased. Okay? Now if I add 100, even more values of brightness will be achieved here. Let's take this, Control C, Control V. Okay? As you can see it becomes brighter and brighter. Okay? And we have some of the details actually has started to disappear and this to be replaced by white pixels. Because actually here we have reached what? The overshooting. Okay? So it will be saturated at the maximum value of 255, which corresponds to the white color. Okay?
If we try to make it darker, it's going to return to its original color.
Actually, as a result of this last addition, some of the information has been lost. Okay? Some of the information has been normalized to be equal to 255. Okay? If I will make it darker, these values that have reached 255, actually they will be reduced to gray levels, darker gray levels. But I will not be able to restore the original image again. Okay? Because actually some of the information actually has been lost. And as you can see from here, of course, if I want to add two images together, as you can see here, this is the original image, this is the second original image, and this is the result of adding the two images together. Okay? Of course, this is a very, trivial way of adding the two images with each other. I can have much more, let's say, better ways that will give me better quality, like, for example, the blending technique or some other more complex techniques. But this is as straightforward, just adding the two images together. Okay? Here, for example, if I will make something like this here, I want to show, we'll see, this same image, but I will subtract from it, let's say, 150. Okay? So as you can see here, it became dark, right? But some of the details of the image actually have been lost. Okay? Why? Because I have reached the overshoot, and this overshoot has clipped the value to 255.
Doctor?
Yes?
If we just, after we convert the image, we didn't add 100.
Yes, yes.
And straightforward, we subtract
Okay.
dark.
We can do it here. Here, let's assume that I have this one. So we'll see. Control V. So in this case, I will add the two images P and Q, the original image, and generate the image R. Okay? And now let's make something like this here. In this case, I will, let's put it like this, R minus 150. Okay? So it will be something like this. Why? Because actually, as a result of the adding the two images, maybe some of the pixels as well has lost its original values because it has reached the overshoot. Okay? So here, if we compare these images together, let's look at the first two images that we have here. This one, and that one. Actually, here the original image used the big circle. It has a yellow color. After the addition, this yellow has reached what? The white color. So this means that the original information about the color has been lost. I have reached the saturation. Okay? But if I want to make a correct addition of these two images, in this case we'll use the blending that we'll see later. In this case, things will be much better. So now, let's go back here to this window. Here we have another example. Let's first of all clear the workspace, close the figures, and clear the command window. And now we'll take this image of peppers. Do you remember this image? Control C. Control V. Here in this case, what has been done is that we have read an image and put it in the matrix V. And the same, this image actually we have added with 100 and put the result with RS. And now we will display both of these two images together. So what I expect actually is that as you can see, this is the original image on the right, and this is the image after adding the offset on the left. As you can see here, we will have that more gray components are added to the image due to the overshooting and all of these things, in fact. So let's go back here to this example. So this is for the example A. If we look at example 3, which is the second piece of code in your chapter, which is about the image subtraction. Okay? Here we have two images, back 1 and back 2. Okay? First of all, we will display them. Then after that, in the image toolbox, in the image processing toolbox, we have a function that's called image absolute difference. Image absolute difference. So this means that it will subtract these two images from each other, and the result of the subtraction, I will take the absolute value. Okay? Then after that, here we will show this image. Of course, I can make my own function that handles this kind of operation. Okay? You can do it your own. Then after that, here what will happen is that when you will show the image, then after that you will get the negation of the image by subtracting the image from 255 and showing this negation. So let's go through this procedure step by step. Here we have the P. Let's close as well, close all, clear, CLC. And consider this example. Here we have, Control C. We have read the two images, back 1 and back 2. Okay? So this is the image back 2, and this is the image back 1. The idea here is to show that, for example, I have this image, actually it represents a certain background, and that image, it represents the same image, but after adding certain objects on the same background. Okay? And we'll see now what will be the result of the subtraction of these two images. So here we will apply this function, which is the image absolute difference, and show the result of this difference. Control V. It will be something like this. Okay? So actually here it can show that I have within this region, the non-black regions, this means that I have, these are the objects that differ from the previous image. So like this, I can detect objects in an image that appear on a certain background, if I have the original image of the background. Right? So this is the resulting of, or the result of the subtraction. For example, if I want to get the negative of this image, just make 255 minus the image. What do you expect to have? Actually, this black part actually will be white, okay? And this values actually, they will have different colors, okay? If it is green here, if I have a green component that is dominant, after making the 155 minus the image, I will have the blue and the red will be dominant, okay? So if this one is green, after subtraction, I expect the color will be something like this here. So here I will make the subtraction. Then after that, we'll show the image. It will be something like this. So here I will have the red and the blue will be dominant, which is the magenta. Right? And here all of this space actually will be white. And the non-white objects here, this corresponds to the objects that were added to the original image in the first place. Maybe they are of different colors, but at least I know their boundaries. Okay? So this is for example B. Now let's look at example C. So the first two examples, we have seen the addition and we have seen the subtraction. Now we look at the multiplication. Okay? Now we look at the multiplication. And if you remember, in each example, we are introducing a new function that exists in the image processing toolbox. Okay? So in the first example, we have seen the IMAdd, which is responsible for adding images. And we have seen as well the IMAppsDiff, which is responsible of subtracting two images using the absolute value. Now let's look at the multiplication. Here in the multiplication, we'll do something which is nice. And here I have an original image and I want to improve the quality of this image. Okay? By sharpening this image. Okay? Sharpening this image means what? Means, for example, that the dark, let's say, region will become darker and the bright region will become brighter. So in this case, I will have a contrast. The contrast will increase. right? So here we have certain special functions, okay, which is called unsharp. Here we have a function that's called f special, and here I will apply, let's say, for example, the type of the function. I will say what is the type of the function. Let's say مثلا here unsharp. And here I will specify a certain parameter that corresponds to this function. Okay? Now, let's look at the different lines that we have. First of all, I will read the image, which is called points.png, put the resulting image in the matrix P. Then after that here, I will generate a filter, Q. Okay? This filter Q actually will see its size now. And what is its relation to the size of the image? Do we have a certain relationship between the size of Q and the size of P or not? Once I have generated this, let's say, filter, I can apply this filter on the image. As you can see here in line 8, I have a function that's called convolution. Convolution 2. This means it's a two-dimensional convolution. So I have the filter is represented in Q, and you will see what will be the content of this filter. And I have the image itself, which is in P. Right? Okay? And we'll apply this filter on the image, resulting in a new image that's called R. This is the image after filtering, after sharpening. Okay? And the next step, it will be just displaying this image. Okay? If special, it will create the filter, yes. Okay? Right? I think you have done the course about signals and systems, right? Do you know what's the meaning of a convolution?
Yes.
Okay. So actually here, what we need to do.
How about the mesh?
The mesh, we'll see what's the mesh. Mesh, this is one way of plotting, let's say, a relationship. So here, the mesh is used in order to plot the surfaces in 3D, as you will see. Okay? But first of all, here, when I talk about convolution, what do I mean by convolution? It's multiplication and shifting and addition and lots of things. But what is the purpose of doing convolution?
It's a button that you constantly.
Yes. Actually here, all of the operations that we are doing here, or the matrix that we are creating, it is in the spatial mode, in space. Right? Okay? And if I want to apply a certain filter, either to enhance, to blur, to detect edges or whatever, in this space mode, in this spatial mode, I can do it with the filter using the convolution. Right? The thing that can be done with convolution in the spatial domain or in the time domain can be done by simple multiplication in the frequency domain, and vice versa. Whatever can be done using convolution in the frequency domain can be done using multiplication in the time domain or spatial domain. Okay? So since here I want to apply my filter in the time domain, in the spatial domain, so in this case I will apply the convolution. But in 2 dimensions. Okay? But in 2 dimensions, I have X and Y. I have, for example, the rows and I have the colors. Right? So, of course, this part we'll talk about in details later, inshallah, when we talk about filtering and enhancement of images and all of these things. But for the time being, I want you to know that we have this type of function, which is called f special. Okay? So, first of all, I will open the image, Control C, and show the image. It is this one, sorry. It is this one. It's a set of kinds. Okay? And in the image, if the quality of the image is fine, okay, but I need to sharpen it more. Okay? I need to have some more contrast. Right? So here we will create our filter using the f special function. Control C, Control V. Okay. Now let's look at the P and the Q and make a comparison between their sizes. طبعا the P here is the original image. As you can see here in the workspace, the first element here is P. It has the dimension of 246 by 300 unsigned integer 8. Right? And this is a gray level image. Right? It's a grayscale image. Right. Here for the Q, of course, here the size is not clear. And here he has shown us some of the elements that exist inside this matrix, but he didn't give me any information about it. So here, if I want to see the content of the Q, just write Q and enter. So here we have, this is the content of the Q. Okay, something like this, right? Here I have values. I have the negative values on the boundaries, as you can see, and the central point here, it has a certain positive value. Okay, it has a central positive value. Right. The idea here is the following: how this filter will be applied on the image. It will be applied pixel by pixel. How? What will happen here, for example, if I have this filter, okay, and I have an image of this size, okay? Inside this image, actually, I have what? Several pixels, right? Okay, and so on. Okay, how the filter will be applied? Here in this case, if I want to apply the filter for this specific pixel, what will happen is that I will get this, let's say, 3 by 3 filter, and I will put it on the image so that the central point of the filter will be coinciding over the pixel that I want to filter. Okay? And the operation of the filtering is very simple. Here, each pixel will be multiplied by the coefficient that is directly above it. So here I will multiply this point by 3.667. This pixel, its value will be multiplied by negative 0.333. This pixel will be multiplied by negative 0.333, and so on. This will be applied for all of the 9 pixels, and they will be added together. And the result of this multiplication and addition will replace this pixel. And this will represent what? The filtered pixel. Okay?
The filter will apply on one pixel only?
It will be applied, this will be repeated for all of the pixels in the image. Okay? I will apply it pixel by pixel. This is what is done by the convolution function. Okay? Of course, here the shifting and the multiplication and the addition and so on, actually here the shifting, or let's say the conversion of this, putting the left to the right and the right to the left, since this matrix is symmetric, actually it will not affect the values that I have. Right? So what will happen here, as you can see, is that I will have this filter that consists of the 9 values. It will be applied on the pixels in this image, pixel by pixel. Okay? How they will be applied? If I want to apply it, for example, on a certain pixel, just put the central value of the filter over the pixel under consideration. Okay? Then after that, make a multiplication between the value of this pixel with its corresponding value of the filter. Okay? And after making this kind of multiplication for all of the 9 pixels, add them together, and the result will replace the central pixel. Clear? After you finish with this pixel, do it with the next one, until you finish with all of the pixels that you have in this image. Okay? This is how the filter is applied on the image that we have. Clear now? Okay? Fine. Now, okay, thank you very much. Very much. Okay. Okay. Here, as you can see, for the f special function, I have the first argument here. It will give me an information about the type of the filter that I want to create. And this, the second argument here, it's an argument that can change the shape of this filter. Okay? It can change the shape of this filter. And for example, here, you can test when you put a 0, what will be the value of the Q, and when you put, let's say, a 1, what will be the value of the Q. Actually, it will give you different types of filters. We'll talk about this, inshallah, in details later. Okay? Right. Okay. Here, if I want to plot this filter, if I want to plot it in the form of, let's say, a graphical plot, of course here, for this filter, we can say that I have rows, I have columns, and I have value for each row column. So how can I plot such type of matrices, two-dimensional matrix? Actually, it can be plotted like this. I will assume that I have, for example, this horizontal level. Okay, I have this is the axis, this is the rows, and this is the columns. Okay, and for each one of these values, it will be represented by the height. Okay, how can I do this using the mesh function? To see how it will be represented, actually, it is very simple here. In this case, actually, it is a small matrix, so the value is something like this. Okay, as you can see, this is a three-dimensional plotting. Okay, so here, as you can see, we have this is the rows, for example, and these are the columns 1, 2, 3, 1, 2, 3, right? And for 1, 1, this is the value that corresponds to it, which is, for example, it is negative 0.33. And for the vertical axis here, you will have the values of the elements themselves. It starts from negative 1, 0, 1, 2, 3, 4. So we'll find that all of these 8 points, we are having the same value, which is negative 0.33. Okay? And I have only the point in the middle, or at the center, that has the value of 3.6667. Can you understand the idea? Okay? So here, in this kind of matrices, if I want to plot it, I will not be able to plot it using the normal 2D graphs. I need to use this kind of mesh. Okay? Clear? Do you have any problem understanding this figure? Right. Then after that, what we need to do is to apply this filter on the image that we have. So we'll apply it using this function, which is called the convolution tool. It's a warning, it's not a problem, but it's working, yani. And we'll see here what will be the result. Control C, Control V. Okay? I have something like this. Okay? What do you think? Here I have a problem. صح? What is the problem here? Actually here, let's compare the P and R. P here is the original image, right? And R here is the image after filtering. What is the difference between them? The first one is of type unsigned integer 8. Okay? But the second one here, it is of double type. So in order to make things correct here, what I should do? Divided by the maximum, okay? So here in this case, either I can divide by 255 directly, or I can divide by the maximum value that has appeared in this image. صح لا؟ خلينا كده نشوف here what will happen. For example, if I will divide by the maximum 255, it will be something like this. Okay? This is the resulting image. Let's compare it with the original one. Where is the original image? Here. We'll find here that the new image is a bit sharper than the original one. Right? If you apply it another time, the same filter on this resulting image, it will become sharper and sharper. But the idea that if you will apply it for a successive number of times, actually, some details of the original image actually will be lost. Clear? Okay? Type. Now, let's look at something else here. What do you think about the sizes of the images here? The original image was 246 by 300. The resulting image here is 248 by 302. Why? اللي حصل عندي هنا. Yes. Actually, it's because of the filter. دي أول حاجة. Okay? In order to handle the filter, if you remember, we have said that if I want to apply the filter on a certain pixel, I need to put the 9 pixels like this and multiply each filter value with its corresponding pixel. Okay? For the pixels that appear at the boundaries, for example, the upper boundary, the lower boundary, the right and left. Okay? For this function to be applied, this convolution function actually it will add lines of pixels. Okay? It will add a line at the top, line at the bottom, line at the left, and line at the right. Okay? So that it can apply the filter on all of the pixels that we have in this image. Understand the idea?
Yes.
Okay? So that's why here we have a change in the size of the image. Okay? Any questions, Emma? If you have a question, just ask. So this is the end of this example. So in this example, we have introduced a couple of things. Here we have introduced the multiplication. And the multiplication actually here is to be introduced by applying the filter by convolution on the original image. Okay? How can I create the filter? Using the f special function. Okay? Now let's look at here actually in this example, which is example number D, is similar to the previous one, but here actually he is just dividing by the maximum of the values that appear in a certain matrix. And if you remember, if I want to get the maximum value that appears in a certain matrix, let's say matrix R, I have two ways of doing it. Okay? First of all, I need to know here R, what is the dimension of R here? It is two-dimensional. Okay? So in this case, I can apply it like this: maximum of R. This will give me the maximum value that exists in R. Or we can do something else. Convert the R into a vector and apply maximum once. How can I convert an R to a vector? Sorry, R, here should be R. Something like this, colon. This actually, it will convert my matrix into a vector. Okay? Then after that, I can apply max on this R. So it should give me the same thing. Okay? Type. Now let's look at the last examples that we have here. Here in the last example, here we'll have the example of blending two images. Here we have, let's close all, clear the workspace, clear the command window. Okay? And here, Control C, Control V. This is the circles. Okay? Actually, as you can see here, this is which type of images? Yes, it's binary, it's black and white. Okay? Let's look at the type that we have here. It's logical. Logical, this means that the bits or the pixels, they are having either the value of 0 or 1. Okay? Type. If I don't have this workspace and I want to get the type of this matrix, how can I do this? We have a function that's called class, and between bracket we can apply the p. So here, if the answer, it will be what? The class is logical. Okay? Type. Now let's look at the other image here, which is Control C, Control V. This is the second image. Okay? Here, what is the type of this image as well? Let's see here. It is class of Q. It's an unsigned integer 8. So this means that this one most probably it's grayscale. Right? So this one is grayscale. Now I want to merge this or to combine these two images together. Okay? We have in the digital image processing toolbox, we have a function that is called image linear combination. Okay? As you can see here, image linear combination. It takes these parameters. Here we have x. This is the factor with which I will make the blending. So here actually it is 0.8, and here 1 minus x, which is 0.2. So this means that the resulting image, it will be 80% of it will come from, let's say, image P2 or whatever, and here I have the 20% will come from the image Q. Right? Okay? Right. Here, if I make something like this, x equals Control C, Control V. This is the ratio that we have. And I will apply Control C, Control V. Here the image that we have is called P, right? And the other image is called Q. So I have 80% from P and 1 minus or x from P and 1 minus x from Q. Right? Now if we press enter, what's the problem here?
It's not the same size.
They are the same size or not? Actually, they are the same size.
Not the same size.
Let's read this error message.
Are not the same size.
Array input arguments to have the same class. So this means that one of them is logical and the other one is unsigned integer 8. So this logical, let's say, image, I want to convert it into unsigned integer 8. How can we do this? No, just with numbers and multiplication and things. And multiply with 255, yes. طيب خلينا نشوف كده مثلا I will call it P2 is equal 255 multiply with P. طيب خلينا نشوف هنا P2 is of which type? Double. فهنا دلوقتي if I will make this combination between P2 and Q, what do I expect to have? Same thing. So what I should do here in this case? I need to convert this P2 into unsigned integer 8. Okay? So in this case, P2, we can say that it is unsigned integer 8 of P2. Let's see here what will happen. Let's look here. Maybe it will succeed or not. Yes, has succeeded. It has now converted to this value. Okay? Now we'll make the linear combination. And now let's see the resulting image. I am sure of R. Okay. As you can see from here, it's a blending. Actually, it has taken 80% from the circles and 20% of the other image. Maybe we can make it other way around. مثلا say 1 minus x and x and see the result. In this case, the one that is dominating here actually is the second image. Okay, in the circles here we have 20%. Right. Let's try something else. P is still logical, right? Actually, this kind of logical images, I can use them as mask. For example, if I'm interested in a certain region and I want to display this region only, okay, of another image, okay? Of course, here this mask, which is of logical type, should have the same size as the original image. So if I will multiply these two images together, pixel by pixel, what do I expect to have? The black pixels that exist here in the P, okay, its corresponding pixels to the original image actually will appear as black, okay? And the pixels here in which we have ones, the corresponding pixels here in the original image will appear as is. It will have its original value. So here let's make it something like this. Here I will call it, مثلا say W is equal to P multiplied by, here I will make pixel by pixel multiplication, okay, by Q. Will it succeed or not? Let's see. It is saying that I have an error. Integers can only be combined with integers of the same class. So in this case here I need to make typecasting. Here this P, I can make unsigned integer 8 of p and multiply the result of this casted value with q, pixel by pixel. Then after that, show this image. What do you expect to have here? Only the parts in which we have the circles are equal to white will appear, and the other parts actually will be disappear. So this type of operations, I can use it in order, for example, if I want to, let's say, put a part of one picture in another picture. Okay? So its corresponding position, I can put it with a black color like this. Then after that, I can make simple addition. Okay? So this specific part can be added to this specific region. Do you understand the idea? Okay? So this is how, in general, it works. Do you have any questions about these examples that we have done together? أرى علامات استفهام. نعم. Yes.
بالنسبة للبارت اللي حق الكونفولوشن إنه النمبر of the pixels will be increased.
Yes.
The number of the pixels زاد by 2. بس إحنا عندنا المفروض يزيد في كل الأطراف يعني.
خلينا نعملها تاني. This one, right? C, I will run it just like this and look at the workspace. Yes, it's here, P and R, right? So actually here what will happen is the following. For example, I have, if this is my image, okay, we will add line of pixels here, line of pixels here, line of pixels here, line of pixels here.
بس هو زاد بس 2.
Yes, ما هو زاد واحد، يعني زاد واحد يبقى زاد 2 في النمبر of columns. واحد زائد 2 كمان في النمبر اوف روز. That's fine. اوكي؟ فهو هيزود لاين من كل باوندري.
هيزود بيكسل واحد في كل
بيكسل واحد بس، يعني هنا مثلا 1 بيكسل، 1 line of pixels here, 1 line of pixels here, and here, and clear؟ عشان هو يجيب الايه so that he can apply the filter on this pixels that appears on the boundary. احنا اتفقنا ان احنا if I will apply my filter, I need to put the filter over the pixel so that the center of this filter will be coinciding over the pixel itself. And I will make multiplication between the different filter coefficients with its corresponding pixels on which it resides. And the result of this multiplication will be added together. Okay? Understand the idea? So here, if I don't have this extra line of pixels, actually I will not be able to apply the filter on the boundary pixels that I have.
اللاين كامل عبارة عن أكثر من بيكسل مش بيكسل واحد.
يس هو أكثر من بيكسل، أوكي؟ بس هو زود لي قد إيه في الدايمنشن ده؟
أكثر من بيكسل.
زود لي بيكسل هنا وبيكسل هنا.
والباقي؟
فلو هنا مثلا كان في عندي أصلا 200 أوكي I have 200 rows فأصبح عندي هنا في row upper row and I have a lower row. Okay? And the same thing can be said here for the column. If I have 300 columns, in this case I will have an additional column here and an additional column here. So it will be 302. Clear? Okay. So we'll stop here and we'll continue inshallah next